Okay. So we are discussing entropy pooling today. Okay. Entropy pooling. As we already know, we are discussing portfolio optimization theories. So it is it is again a portfolio optimization method, and it is quite, similar to black letterman, but very much different from black letterman. Similar in what way? Basically, it also implements views. Okay. So basically, not implement. It basically incorporates views. Okay. Like black letterman, it also incorporate views. Okay. Now in black letterman, you are having views on so in black letterman, you are having the views on expected return, right? But in entropy pooling, you can have your views on anything, basically mean of return. Okay, mean return, so basically expected return. You can have the views on the price as well. You can have the view on risk factor as well. What are the risk factor? Risk factor basically means volatility, right? Skewness, right? Kurtosis. So these all are kind of risk factors. So in entropy pooling, you can have views on return, price of this stock, views on risk factor as well. Okay, views on basically and another type of view factor is CVAR. Okay, I will discuss in detail in today's lecture. So you can have views on several other factors. Okay, so entropy is another portfolio optimization method in which you can incorporate your views. Okay. Now another benefit. So and then how is it different from black letterman? The difference lies in the fact that in black letterman, basically you assume normality. Okay. So you assume that the market equilibrium returns follow the normality. Okay. But in entropy pooling, any probability distribution. Okay. So it should it so uh, doesn't matter whether your probability distribution of the return is normally distributed or not. So any probability distribution will do. Okay, any probability distribution. So yeah, so that is one of the benefit of entropy pooling method. So in black determinant, as we saw, that black determinant assumes that the returns are normally distributed. But entropy pooling can be used for any arbitrary market model. Okay, so any arbitrary market model. Great. So till now we are building the intuition for entropy pooling. Okay. Now let us just kind of discuss one matrix. Okay. So let us discuss. So in today's lecture we'll be discussing an example, and before we discuss that example, let us just take five stock. Okay. So let us take a stock A, B, C, D, and E. Okay. And then I am currently having my views on so this matrix is kind of return matrix. Okay. And you run Monte Carlo simulation. Okay. So in simulation, you get different type of scenarios. Okay. So you get different type of returns. So for example, let us say I ran the Monte Carlo simulation 1,000 times. So from 0 to 999. So we ran Monte Carlo simulation this much time. Okay. Now, for the Monte Carlo simulation, for the first, this is the first Monte Carlo simulation, right? Let's assume that the expected return of A is 3.5%, B is 6.7%, this one is 2.1%, this one is 12.8%, it can be 9.3%. Okay. Similarly, this is the second Monte Carlo simulation. So, and this is the expected return for A. This one is the in this column, you will have expected return of B. In this column, you will have expected return of C. In this column, you will have expected return of D, and in this column, you will have expected return of E. Now you see you are getting expected return of A 10,000 times. So these are 10 different scenarios. Okay. So what does scenario mean? Scenario basically means that based on different paths that the market can follow. Okay, so you are basically kind of running a simulation. So what will happen if the market follow this path? What will happen if the market follow this path? What will happen if the market follow this path? So basically you are basically kind of creating different scenario. So here you are creating 10,000 scenario, and by creating 10,000 scenario you are getting 10,000 different returns for A. For example, it can be 2.1, it can be 9.6, it can be 13.7, it can be 20.0. So you are kind of simulating different type all possible scenarios that can happen with A. Okay, and from there you get the expected return of A. Okay, so similarly you will have 10,000 scenarios for B, you will have 10,000 scenarios for C, you will have 10,000 scenario for D, and you will have 10,000 scenario for E. Okay, now this one, this zero, this is the first scenario. So in the first scenario you are A is having basically a return of 3.5, B is having a return of 6.7, C is having a return of 2.21, D is having a return of 12.8, and E is having a return of 9.3. Okay, so this is a kind of joint scenario, right? So this is the first scenario, and the first scenario you are having five different stock, and for all the five different stock you are having their return. So it's kind of joint scenario. So now this matrix is called basically R matrix. Okay, this matrix we call R. Okay, now remember, what is the size of R matrix? The size of R matrix will be S into I. Okay, what is S? S is basically the number of scenarios. Okay, S is basically the number of scenarios, and I is basically number of assets. So the size of R matrix is S into I. Now you will have a probability distribution P. Okay, and this probability distribution will be telling you what is the probability of the first scenario to happen, what is the probability of second scenario to happen, what is the so here in the first scenario, what is the probability of the first scenario, and what is happening in the first scenario? In first scenario, the probability, the return of A is this one, return of B is this, return of C is this. So what is the probability of first scenario? Let us denote it as P1. Similarly, this is the second scenario. In second scenario, A is having a different probability, B is having something, C is having something, D is having something. So basically, we are having a joint probability. What is this probability denoting? This is the joint probability that the return of A is 3.5, the return of B is 6.7, the return of C is 2.1, the return of D is 12.8, and the return of E is 9.3. Okay, got it? Now, similarly, we will have P2. Similarly, we will have P3. P3 will be the probability of scenario 3 to happen. Similarly, we will have P9999, right? Now, what is the size of P matrix? Can anyone in the meeting tell? What is the size of P matrix? Anyone? P is the probability
S into 1.
distribution of R. Very good. You see S into, right? So basically, we are having S scenario. So we will have the probability of all the S scenario. So this is the probability matrix. So till now we got to know about R and P. Okay, so we got to know about R, and this R was the return matrix, right? And uh, this P is the probability. So this is the probability. Now this thing we call as prior. Okay, so this is our prior distribution. This is our prior distribution. What is prior distribution? So am I audible, everyone? Guys, am I audible?
Your voice is cracking.
Hello.
Sir, and your screen
Am I
share
audible
has been
now?
turned off.
Yeah, screen sharing. Yeah, just a minute. So basically, we were having two matrices, it is basically R and P, and so this is a return. So basically, you are having 10,000 different scenario, you are basically 20,000 different scenario, and this is the probability which is telling what is the probability of each scenario. This is our prior distribution. Why is it called prior distribution? Because you are having this is the market expectation. Okay, so this is what we call prior distribution. Then you add your views. Okay, and then you get your posterior distribution. This is how entropy pooling works. Okay, now you have a view. Okay, so now you have a view, right? So what is the objective of entropy pooling? So let us see. So the objective of the entropy pooling is that the posterior distribution minimizes the relative entropy between the relative entropy to the prior. Okay. So basically, what is the objective of entropy pooling? So basically, you find a probability distribution Q which is as close as P, which is as close as P, that also incorporate the views. Okay, so but also incorporates the view. So basically, this is a prior distribution. This P matrix is a prior distribution, but now you have added the view. Okay, so now you have added a view. Probability distribution will change because now, since this was the probability distribution of the market, but you have added some view, so this matrix will change. Now you will get a posterior distribution, right? That entropy pooling is a method which gives you posterior distribution. It remains as close as the earlier distribution. It remains as close as the prior distribution while also incorporating your view. This is the objective of the entropy pooling. So the posterior distribution minimizes the relative entropy to the prior while incorporating the view. Okay. Got it? Now, what is relative entropy? We will discuss it in detail. Okay. Now, let us suppose when P and Q are equal. So basically, your prior distribution and your posterior distribution are equal. It means that the relative entropy is zero. Okay. The relative entropy is zero, and the two distribution basically coincide. Okay. That means when will it happen? It will happen when your view is basically equal to P. So when you agree with P, so P is your prior distribution and you are adding some view, and that view is basically the P matrix only. So basically you are agreeing what is happening in the market. So basically your view is in agreement with the market historical distribution. So in that case the posterior distribution will P only because you want to remain as close as P. Okay. So this is one case. Okay. But generally your view will be different from market historical result. In that case, Q will be different from P. In that case, Q will be different from P, but Q will try to remain as close as P. Okay. So the distance of Q and P will try to be as equal as lesser as possible. Okay. So that distance is characterized by relative entropy. So now let us discuss what is this relative entropy that we are discussing. Okay. What is relative entropy? Okay. So let us just assume this is the this is the this is the posterior distribution F bar and F is your prior distribution. Okay. So the relative entropy between these two is basically calculated as the integration of Fy bar ln of Fy minus ln of Fy, okay, and dy. So this is basically the relative entropy between posterior distribution and prior distribution. So you can characterize it as a distance. Okay, so it is not a distance as in because the distance between f and f bar should remain equal, but when you will calculate the relative entropy, it will not be equal. So just make it kind of analogous to distance. Okay, so the relative entropy between the posterior distribution and prior distribution is defined by this formula. Okay, got it? You know, this is matrix Q basically. This is the matrix Q, and this is Fy is basically matrix P. So Fy is basically the prior distribution, and F bar Y is basically posterior distribution. So now what is your objective? You want to find a F bar such that the distance between, so the relative entropy between F and F remains as low as possible. So you basically you want to minimize this entropy. This is the purpose of entropy pooling. Okay, so you want to find a posterior distribution F bar such that this formula remains become minimum. Okay, the relative entropy become minimum. This is relative entropy between F bar and F. Okay, got it? So basically let us assume, so basically what is F and what is F bar? F is your prior distribution and F bar is your posterior distribution. Now let us suppose F bar is your distribution, that is F plus your view. Okay, so basically it is having the mark, it is formed by combining the market historical return plus combining your view, and you get the F bar. Okay, now let us suppose you have multiple F bar that is possible. So basically V is a set of all F bar. So basically F1 bar, F2 bar, F3 bar, okay, F4 bar. So basically there are many F bar that satisfies your view. Okay, got it? So which F bar should you choose? You will choose that F bar which will give you the minimum distance. Basically arg minimum of F bar is equal to arg minimum of G and F. So basically you will choose that F bar from this set. So all this F bar is satisfying your view, but you will choose that F bar which is giving you the minimum distance from F, which is giving you the minimum entropy from F. And how you calculate the entropy from F? Using this formula. Okay, now let us simplify it a bit. Let us make it a bit simple. Okay, so basically we are finding the posterior distribution Q, which is basically the minimum of all x. So which is basically the minimum of all x from the formula ln x minus ln p. So basically you want to minimize this distance, right? So you want to minimize this this is the distance, this is the relative entropy. You want to minimize this entropy, so that x which minimizes this entropy will be your Q. So basically you will put several x into this formula, and whichever x will give you the minimum value, that x will be your posterior distribution Q. Got it, guys? Got it, everyone? P is your prior distribution. There are several x which is satisfying your views. Okay, so x is basically your posterior distribution. Now you will be putting all x into this formula, and whichever will be giving you the minimum entropy. So this is the entropy. Whichever x will be giving you the minimum entropy, that will be your posterior distribution Q. That is entropy pooling for you. Entropy pooling is a, a portfolio optimization method which gives you a posterior distribution after combining your views with a prior distribution, such that the relative entropy between the posterior distribution and the prior distribution remains as small as possible. This is the mathematical objective of entropy pooling. Everyone got it? Then I will move ahead from here. If you don't get it, just ask me. I'm waiting for your question. I got it?
Yes, sir.
Okay, very good. So if I summarize, you are having a matrix R, which were having 10,000 different scenario, and basically giving you possible return of all the 5 assets. And now there will be a probability matrix P, which is the prior distribution, which is telling you what does the historical return say, about each scenario. So what is the probability of each scenario to happen? That is your matrix P. That is your probability distribution P. Okay. So that is your prior distribution. Now you are adding some view. Okay. And after adding your view, you get a probability matrix. So probability matrix Q that will having the same size as that of P. So basically the Q matrix will have a size of S into 1. Okay. Same as that of P. Now, if your view is in agreement with the market historical return, then Q will basically be P only. But if your views are slightly different, then Q matrix will change. But then entropy pooling gives you a method to give you the matrix Q. How do you get the matrix Q? You get a matrix Q in such a way that all the matrix that satisfies the view will be called X. Now they will be put into this formula which calculates the relative entropy. Now that matrix Q will be the answer which is giving you the minimum relative entropy. So basically the uh, minimum of X transpose into ln X minus ln P. X is a posterior distribution that is satisfying your view. P is the prior distribution, and so X there can be several X that satisfy you, but you will select that Q which is giving you the minimum distance from the B. So you want to remain as close as your prior distribution. Okay. So that is the concept of relative entropy. Now, since you have given
If we
some view, hello,
hello, if we change the value of x, then the views will also different now.
no, actually, suppose that you have given some view, okay. Now, suppose you have given some view, so that view can be satisfied by many matrix X, okay, got it? Hello, 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 am I audible? Hello,
Yes, you are audible.
okay. Aditya, you were asking the question, I guess, no? Aditya, are you there? Okay. Okay, anyway, I will contact him. Okay, so basically, this is your matrix Q. So now you are giving some view. So what is your view? Your view is basically Gx. Just a minute. Your view is basically Gx is less than equal to H and Ax is equal to B. Now you will be a bit confused. Okay, how are we defining our views like this? Okay, so your views may be equal. Equal in the sense Equal in the sense you are telling the return of asset A will be 9.6%. In this case, your view will be denoted by this matrix Ax equal to B. In case you are telling the return of B will be lesser than equal to something, then your view will be like this. So basically, you are essentially solving this problem. Q is equal to minimum of this relative entropy subjected to the condition that Gx is lesser than equal to H and Ax is equal to B. What is G, H, A, B, and X? X is basically your posterior distribution. Okay. A and B, I will be telling shortly what are A, B, G, and H. Basically, A is suppose that you are having your view on A, return of A. Okay. Then A matrix will have a return column. Okay. Here you will have a return. Okay. Now, and suppose you are saying that return of A is 3%, then your B will be like 3 over here. Okay. So that is how denote. So basically Gx is lesser than equal to H and Ax is equal to B is for your views. Okay. I will be, when we will discuss an example, I will be telling you how do we construct this matrix, basically A, B, G, and H. They are the input to the entropy pooling. So I will be discussing it in detail, but as of now, just kind of understand that now we have to solve this numerical optimization problem. Okay, we have to solve this numerical optimization problem wherein you have to find the minimum of this value subjected to the condition that Gx is lesser than equal to H and Ax is equal to B. X is basically your posterior distribution and all these are view. Gx is lesser than H is your view and Ax is equal to B is also your view. Okay, got it everyone? Got it, everyone?
Yes.
So before, before discussing how to find this, let us start discussing an example, and I hope that will help you to, understand everything in more detail. So before, yeah, okay. So here you see, this is, by courtesy of uh, guy from, Fortitude Tech. Okay, Fortitude Tech is a company that helps you to evaluate entropy pooling. So it is the, package of that company. Okay, so basically, what they are showing through an example is, they have taken 10 asset. Okay, so they have taken 10 asset over here. Just a minute. They have taken, okay. Now, let us discuss. These 10 assets are government and MBS, Corp IG, Corp HY, EM debt, DM equity, EM equity, private equity, infrastructure, real estate, and hedge fund. These are the 10 assets they have taken as an example. Okay. Now, the R matrix will be, in this case, your so the R matrix that we have discussed by RDF. Okay. So the R matrix is basically RDF. So they have taken 10,000 scenarios. Okay. They have taken 10,000 scenarios to 9999. Okay. And basically these 9 assets. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is your R matrix. Okay. Now, here you will be having the return. So return from the 0 scenario. So return from the first scenario, second scenario. This is a 10,000 scenario. Okay. So basically you will having a return matrix over here. So what is the return of 0, 1? What is 0? 0 is basically government and MBS. So these are the 10 assets, and these are the 10,000 different scenario, and R is your matrix. Okay. So this is basically the return matrix. So you will be putting the mean of 0, return of 0, here return of 1, return of 2, return of 3, return of 4, return of 5, return of 6, return of 7, 8, and 9, right? Okay. Now, this is your matrix R. Okay. Now you convert it into, so what is the size of R? Anyone? What is the size of R?
1000 cross 10.
10,000 cross 10, right? Yes, very good. Now let us start further ahead. So basically, this is the, this is the basically result from the historical data. So basically, this is the code that they have calculated. So simulation moment. Okay. So mean, volatility, skewness, and kurtosis. So basically, you can get it from moment. They have used Fortitude. Take the package. You can use several other packages that is available in Python to calculate mean, volatility, skewness, and kurtosis of the, historical data, from the historical data. So basically the historical data, the scenario data they have used, they are getting the mean of government and MBS is 0. Minus 0.70. The mean return of Corp IG is minus 0.40. So this is matrix R. Okay. Now, if you see, the basically you are from this so we are basically writing that matrix that we have discussed, was RDF. Okay. So that was basically the size was 10,000 cross 10. Now we are converting it into an array. Okay. So R is an array. Okay. So numpy array basically. And then we are assigning S equal to R into shape of 0. Okay. That means, so basically what is R? R is having basically, so R is something like, so you are basically having 10 rows. So R is basically not having 10 rows, 10 column. And between each, shape, you are having 10,000 different scenario. So here you are having 10,000 different possible return for asset 0. Here you are having 10,000 different possible return for asset 1. Similarly, you are having 10 different type of this materials. So 10 different type of array. So R is basically an array of array. Okay. So this is not difficult for you to analyze. And now you are assigning S as R dot shape of 0. So this is R of 0. So this is R of 0. Just a minute. R is basically 10,000 over here. So S is basically 10,000. Okay. Shape of 0 will be 10,000. Okay. And then P is equal to NP dot ones and S into 1. So basically you are having S row and one column. Okay. S row and one column, and NP dot ones means assign one to every row, assign one to every possible place. So this is basically your P. Now you see you are dividing by S. So basically this is 1 by S. Okay. So this is your prior distribution P. So you are having the RDF matrix that was having the 10,000 different scenarios. Now, what is the probability of each of the 10,000 different scenarios? The probability is 1 by S. Basically, you are multiplying here, right? So that is your P. Got it, everyone? So RDF, you know what is RDF? RDF was basically having 10,000 different scenarios and basically 10 different assets. And P is basically the probability. Here they are taking equal probability for all the events. So basically you are having 10,000 different scenario, right? So the probability of first scenario to happen is 1 by 10,000. So here they are taking equal probability for everything. Got it? Basically they have divided by S over here, right? So this is the P matrix for you. Got it, everyone? Everyone got it till now?
Yes.
Yes, sir.
Now means prior. Okay. So what is means prior? It is telling you what is the prior return of one asset. What is the prior return of one asset? So basically, see, R was having like this, right? 10,000 different scenario for each asset, 0 to 9. Now means prior will be giving you one return for every matrix, so for every asset. Now you tell me one thing. Let us forget 9 asset. Let us forget 9 asset. Let us worry about asset 1. Asset 1 is having 10,000 different possible return. Okay. Asset 1 is having 10,000 different possible return, right? So here is asset 1 and here you will be having return of asset 1. And you are given the probability of all the possible return. Okay. So basically let us say 2.6%, 3.1% is the return, 9.6%. And here you are giving the probability 1 by 10,000, 1 by 10,000, 1 by 10,000. Then what will be the mean return of asset 1? What will you do to calculate the expected return of asset 1?
Multiply return with the probability.
Very good. So this is the concept of expectation, right? So this is the 10,000 different possible. So this is basically your random variable. And this is your probability. To get the expected return of asset 1, what will you do? You will multiply the probability with the random variable. And that is what we are doing over here. So basically, P into T means P transpose. So P transpose into R. So basically, you are multiplying the matrix. So that is how you get the means prior. Okay. So let me explain it once again. What will be P transpose? P transpose will be 1 by 10,000, 1 by 10,000 to 1 by 10,000. And this is your matrix R. Here you are having 10,000 different possible scenario. This is for asset 1. This is for asset 2. Similarly, you will have 10 different assets. This is basically 10,000 different scenario. Now, when you will, how do you do matrix multiplication? This is how you do it, right? This into this. So when you are multiplying these two matrices, you are basically getting the mean return of asset 1. When you are multiplying this matrix and this column matrix, you will be getting the return of asset 2. Got it? And that is how you get. So this is 10 into, this is 10 into 1, sorry, 1 into 10, right? And this is 10,000 into 10. So when you multiply this, just a minute, this is 1 into 10,000, sorry. So when you multiply these two metrics, you get a matrix which is 10,000. So basically you get the expected return of all the 10 assets. Got it? Got it? How you are getting the expected return of 10 assets, everyone? So basically means prior is nothing but a single row matrix 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here you will be having expected return of asset 0, asset 1, asset 2, asset 3. So this is your means prior. Got it, everyone?
Yes, sir.
Yes, sir.
This seems like kind of like the Markovitch analysis.
Could you please repeat?
This kind of seems like the Markovitch analysis.
Yes, Markov analysis. Basically, you are having 10,000 different scenario for each asset. Now, for each asset, for example, let us say asset 1, you are having 10,000 different possible return. And for each possible return, you are given the probability. Then how you calculate the expected return? You just multiply them. And this is the multiplication that we are doing. So for asset 0, there was 10,000 different possible return, but this is the expected return. So so at a random variable can have many possible values, but you can get the expected value by just weighting them with probability. That's how we do it here. And here similarly, you are calculating the volatility. Volatility is nothing but basically probability transpose into R minus expected means prior, basically the expected return into its square root, and then it's into its square, and then it's a square root. So this is basically a volatility, prior volatility. Okay, so prior volatility will be, you will be having the volatility of each of the asset. So it is also a 10 in one row and 10 column matrix. Okay, is everyone getting how are we doing this? So this is basically the same formula. Volatility is equal to x minus expectation of x square, nothing else. How? Let us see. This inside thing is this one, and then when you are multiplying them with the probability matrix, you are calculating the outer expectation. So this is nothing but your volatility. Got it? Got it, everyone?
So basically, from each column, we have to subtract the expected value and then multiply with the probability and then square it, right?
Exactly. So basically, you once you have calculated the expected return. So basically, this is the matrix R, right? So R matrix is like this. For each asset, 0, 1, 2, 3, 9. For each asset, you are having 10,000 different scenario. So now what you are doing, you are basically subtracting the mean return of 0. So mean return of 0 you can get from means prior. So let us say the mean return of 0 is 3.5. So then you will be subtracting minus 3.5 from all the scenario, right? Got it? So now once you subtract it, you are basically squaring it. So after subtracting, you are basically squaring it. And after squaring, you are basically calculating in the expectation. Same as that of, this is the formula for variance, right? And now you are taking the square root to get the volatility. Same as that of the expectation concept. Got it?
Yes.
Yeah. So now you have calculated. So after this step, you have calculated what is the mean return of each of the asset and what is the mean volatility of each of the asset. Got it? Now, let us see. Mean rows. Yeah, just a minute. I guess we have missed the. Uh, we have missed an important slide, I guess. Okay, no, we are having here. So see, we then what is our view? So let us see what are our view. So the view is mean of private equity is 10%, volatility of EM equity is less than equal to 20%, a skewness of DM equity is less than or equal to minus 0.75, kurtosis of DM equity is greater than or equal to 3.5, and correlation between corp HY and EN debt is 50%. So these are your views. Okay, got it? Now, see, in this view, you are having equal sign. So this will go to X equal to B wala matrix. In this, you are having less than or equal to. So this will go to GX equal to H matrix. In this, you are also having less than or equal to type view. So it will go to GX is less than H matrix. Here you are having greater than or equal to. So you can convert it into less than or equal to. For example, X is greater than 3.6. So you can convert it into minus X is less than equal to minus 3.6, right? So when you multiply both side by minus sign, this sign changes, right? So you can convert it into less than equal to, then it will again go to Gx is less than H matrix. And then correlation between corp Hy and EM depth is 50%. So it will again go to Ax equal to B matrix. Okay, got it, everyone?
Yes.
Now we are having our views on mean, volatility, skewness, kurtosis, and correlation. So we have to calculate these 5 metrics because A will be this matrix. So basically A will be mean matrix, volatility matrix, skewness matrix, kurtosis matrix, and correlation matrix. B will be the value that each view is giving. So basically the mean of private equity is 10. So you are having B as 0.1. What is the next equality sign? The next equality is correlation between corp Hy and EN, that is 50. So you are having 0.5 over here. So this is a B matrix. And A matrix will be the matrix of mean or volatility or skewness or kurtosis and correlation. We will see it in detail. But now, as of now, let us discuss what are the equality constraints. What equality constraint are? Mean and correlation, right? Mean and correlation are having equality. So they will go to X equal to B. Now, so if we see what are the assets that are involved, just a minute. Assets which are involved are private equity, okay, private equity, EM equity, EM equity is here, and then we are having DM equity, DM equity is over here, and then we are having Corp HY and EM debt, Corp HY and EM debt. So we see only these metrics are involved, only these 5 assets are involved, okay. So we won't trouble other, metrics. So why to make our computations, difficult? So we'll just be dealing with from 2 to 7, right? So this will be our matrix. So 2 to 7. 7 is not included in this type of notation in Python. So we will basically be dealing with 2 from 2 to 7. Got it, everyone? We will not be taking other asset into account. Okay. So now we will be calculating mean first. Okay. So what are the mean rows for asset from what are the mean rows? So we were taking account from asset 2 to 7, right? So the mean rows will be, this is the matrix R, 10,000 different scenario, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you are basically taking only this portion by this. So we are basically doing R. What does this mean? This means all columns. So you are basically considering all column, but rows from only. So basically this means all rows. So you are considering all the rows, but columns only from column 2 to 6. Okay. This is the two. Now you are basically transposing it. So now what will happen when you transpose? You will get a matrix mean rows. So what will be the mean rows matrix? Let us see. So the matrix mean rows will be here for the asset 2, 3, 4, 5, and 6. And here you are having 10,000 different scenario. Okay. Basically, you have transposed it here, right? So that is why it is transposed. Transpose means rows become column and column become row. This is the mean row. So basically, row. Okay. Uh, so we are calculating volatility only from asset. So we are excluding asset 7. So we are basically excluding asset 6 from volatility. Why? Because you can see asset 6 is private equity. So private equity. So we are not having any view on volatility. Okay. So we are excluding asset 6 from volatility. Okay. So that's why we are calculating volatility only for the asset from 2 to 6. So how will volatility rows look like? It will look like, so this will be volatility rows, and it will look, so see, this will not be there. Only 2, 3, 4, 5 asset will be there, and you will be here having the volatility of each of the asset. Okay. And 10,000 different scenario means what is the volatility of asset 2 in the first scenario? What is the volatility of asset 1 in the first scenario? Okay. Similarly, you can, so here you can see you are calculating the skewness only for the asset 3. So this is 4. So wait, you are calculating the skewness only for the asset 4. Why? Let us see. Basically, you are given a skewness of DM equity is less than or equal to minus 0.75. So a DM equity is asset 4. That is why we are only taking asset 4 as here. Similarly, we are taking kurtosis only for asset 4 because we are comparing kurtosis only for asset 4. And then we are calculating the correlation between asset 2 and asset 3 because in our view, he has given correlation asset 2 and asset 3. So this is our metrics. And what are these metrics? These are the metrics that will help us to get A and Z. So A and Z. Okay. Now let us see how we are getting matrix A. Okay. This is the matrix A. How we are getting matrix A? Let us see in detail. First of all, the relation is X equal to B, right? So here you will be having asset 1. You are having 10,000 different possible scenario. Okay. Okay. So it will be having some size into 10,000. And you are having asset X. So it will be something like 10,000 into 1. Remember, what is this X? This is your posterior distribution. So this will be the probability of the posterior. So this is a probability matrix. Okay. X is a probability matrix. And then you will be having some B. Now let us see how we are building up. Okay. So here X is will be X1, X2, X3, X4, X5. First of all, what is B stack? B stack is something like you are vertically stacking some array. Okay. So let us say B stack. So let us say you write something like np dot B stack 1, 2, 3, and then 4, 5, 6. So basically this will vertically stack 1, 2, 3, and then 4, 5, 6. Got it? It will only happen if you put equal column. So here column number 3, column 3 column. So it will vertically stack all the inputs that you give. Similarly, this np.b stack will vertically stack this matrix, this row matrix, this row matrix, this row matrix, and this one matrix. Okay, got it? So let us see how we are getting A. First of all, what is this one? Np dot ones of 1 and s. That means it is basically nothing but one row and s column. One row and s column. What is the value of s? Everyone knows, right? The value of s is 10,000. So you are basically putting 10,000 times. If you have written np dot zeros, that means you will having 0 every time. So this is basically the first stake, right? So you let us stake it here. 1, just a minute. 1, 1, 1, 1, 1, 1. Now if you see, when you multiply it, this is the A, and when you multiply it by X, basically you do it by this, right? When you multiply it, what will you get over here? This will be 1 into x1 plus 1 into x2. You know multiplication, right? 1 into x3 into 1 into xn. What will be its value? Can anyone tell?
So
Anyone?
1.
Very good. This will be 1. Because this is a probability matrix, right? X is your posterior distribution, your probability matrix. So this value will be 1. Because you take 1 common and then it will be x1 plus x2 plus x3. So it will be 1. So this is your B matrix. So correspondingly, in B matrix, you have, here you have written 1. Why we are staking it? So let us see. Similarly, we'll be staking something over here and we will be staking something over here. So first we have stacked np.1s 1s, and then you have stacked 1 over here. Okay, got it? Now let's move forward. Now this is mean rows. Okay, so this is basically the mean rows. You know what is mean rows, right? Let us see what was mean rows for us. Mean rows was nothing but A, this was having for 10,000 different assets. So it was basically the transpose, right? And for from the asset from 2 to 6, 2, 3, 4, 5, and 6. So this is your mean row. So now you are staking over here. Now you are staking it over here. So let us say its value are, so how do we stack? So let us see, this one is the mean row, okay? So you take it from here and you place it over here. So you are basically staking. So see, you are having 10,000 different column. Here you are having 10,000 different column. So this value you are putting over this first. So let us see how do we stack. So let us say here you have written A, B, C, D, E, F something. So here you will have A, B, C, D, E. And then let us say you are having capital A, capital C. So this is how you stack, okay? So same to same stacking is happening. So after the first stacking, you have stacked mean rows. Did everyone understand how will the mean rows be? How is this stacking looking like? Everyone? So this is your matrix A. First of all, you have staked the ones, and now you are staking mean rows. So you have staked mean rows. Got it, everyone?
Yes, sir.
Yes. Now, what will be a stack over here? This place. Everyone, let us discuss. This is interesting. So we are there are basically five assets. Okay, 2, 3, 4, 5, 6, for which we are expressing mean. Now, for this sixth asset, which is private equity, you are saying that the mean of private equity is 10%. Got it? Okay. So this sixth asset, for this asset, you are saying its mean is 0.1. Okay. So now let us see how you will do with this. Here you are having 1, 2, 3, 4, and 5. So this is for asset. This is the mean return of asset 2, 3, 4, 5, and 6. You are having a view, right? Your view for this sixth asset is that its mean is 0.1. So you will put 0.1 over here. Now what will happen with this one? Here you will be putting the prior mean. That is the mean that was for this asset. So you have calculated a prior mean, right? Means prior. 0, 1, 2, 3, 4, 5, 6, 2, 8, 9. So this matrix, this means. So you are having a prior mean for this matrix, right? So you will be putting prior mean over here. So from 2 to 5, you will be putting their prior means, and for 6, you have, so from 2 to 5, you have not given any view. So that is why they will be remaining with their prior view. So let us say it was basically A, B, C, and D here. So you will be putting the same value. But for 6, you are having a view that the return of 6 will be 0.1. That is why 6, this place you have changed it to 0.1. Got it, everyone?
Yes, sir.
Now let us see once, okay? Let us see an interesting thing. So this is for asset 2, okay? So now this is the posterior probability distribution. So now when you multiply the return ABCD for asset 2, so A into x1 plus B into x2 plus C into x3, you will be getting your earlier return only. This is your earlier return only. So because you have not, so that is the beauty of entropy pooling. You are not changing its return because you have not expressed its view. So your posterior probability distribution will also give you that same value that you are having earlier. So the mean return of A will remain same. The mean return of basically asset 2 was A in the earlier probability distribution P. In the final probability distribution Q, its mean return will remain A only. For the asset 3 also, its mean return will remain B only. For asset 4 also, its mean return will remain C only. Similar, but for asset 6, its mean return will change to 0.1 because you have expressed a view, and that is what this matrix Q will be satisfying. So this matrix Q is satisfying this view. Now you are having some view on volatility. So we see this is the same thing. So this is basically we are staking 2, 3, 4, 5, and here we are staking 0.1 separately. Why? Because we are having a view on it. So this is basically B. So we can, when you see the code A and B, you can understand this in detail. Let's not go into that much, kind of deep. But what we can understand this from Ax equal to B is when you are having some equality kind of view, then you stack, for example, you are having a view on mean, then you stack the mean matrix over here. This is the probability distribution, and this is the mean that you get. Okay, got it? Similarly, when you are having views like less than equal to, then you express it in, so then you put it into matrix G and H. So let us see, then you will understand. The first, less than equal to, the first view, volatility of EM equity is less than or equal to 20%. Which is, so volatility of EM equity is less than equal to 20%. What is EM equity? 5, asset 5. Let us see. I will again repeat. Volatility of EM equity is less than equal to 20%. So see, this is the volatility matrix, and this is the, that you have put basically 0.2, right? 0.2 square because variance. Similarly, the next is skewness of DM equity is less than or equal to minus 0.75. So in G, basically you are putting a skewness matrix, and in matrix H you are putting the result, that is minus 0.75. Okay. And from where are you getting the skewness matrix? This is the skewness row. Basically, this is for asset that you are discussing, asset 4. So you have basically expressed your view on asset 4. That is why this is the skewness row, and this is the, so this is the matrix, and this is your result view. This is your view. Got it, everyone? See, this is quite complex. So once you go through the code on your own, then you the metrics on which you are expressing your view, basically the mean, basically the volatility, skewness, kurtosis, and correlation. And this matrix will go to your A or G. And then you are having some view, right? Less than 20%, greater than 20%, 0.1. And that will go to basically matrix A, basically matrix B or H. Got it? And then the posterior distribution combine your view and give you a result. So this is a posterior distribution. So basically when you say that mean of asset 1 is 20%, so this is the mean matrix, this is the probability matrix, and this is B. So basically it will give you like mean of asset 1 is 20%, so this will give you 20%. This is the matrix mean, and this is basically the probability distribution. So that is how you multiply and give you the result. So this is the entropy pooling for you. Any doubt? And now just one last section. So there will be several matrix X that will be satisfying, but there will be an X which will be giving you the minimum entropy, right? So we have discussed it in detail over here. So basically so this is the entropy pooling function. You supply the earlier probability distribution P, you supply A, B, G, and H, and then as the result, you get a matrix Q, which is your posterior distribution. This is the matrix Q. Okay. So this is an inbuilt function. So you don't have to optimize the numerical function by yourself, and then you can calculate the relative entropy as well. So you have got Q, right? So now you can calculate the relative entropy. So this is nothing but Qt into log Q minus log P. So this is the relative entropy. Got it? And so earlier you were having mean volatility, skewness, and kurtosis based on historical return, right? This is the basically mean volatility, skewness, and kurtosis after you have incorporated your view. So you can calculate it using the code that has been given here. I will share this code, and this is your basically having the correlation matrix. Got it? Got it, everyone? So after you incorporate, so earlier, let us see. This is the private equity, right? So after you incorporate your view, your mean return is 10%. Let us see what was it earlier. So before you ever expressing your view, it was 13.70%. Okay, got it? Got it, everyone?
Yes, sir.
Any doubt?
Yes, sir.
Only there, two people are there in the meeting. Okay, I know very less people have survived. So did you guys understand? So basically, what is the basic intuition behind entropy pooling?
We incorporate our
You
own
can,
views on
being a
the
driver and
historic.
you can understand the code and how to implement it. But the basic intuition should be clear. You got the basic intuition, right?
Yes, sir.
Okay. So do you have energy to, discuss 5 more minutes, or should I end it here?
I think we should go through the code once, then only like it will be better.
No, the code part is complete. I will only discuss the numerical optimization part. So how does the code actually calculate the, if you guys allow me. Otherwise, let us
Yes,
discuss
so you
after,
can.
some. Okay, I will take just 1 minute and then I will end. So it will. So let us just see. So this was our numerical problem, right? So basically, we are finding Q as our minimum of all X, which is satisfying XT transpose ln Q minus ln P, right? And basically, subject to the view that you are having a view X equal to B and Gx is less than H. Okay. Okay. So how to find the solution of this problem? So basically, we construct Lagrangian x lambda. So the Lagrangian is basically an approach that helps you to calculate the. So that helps you to numerically solve a problem given some constraint. Okay. So how do you formulate the Lagrangian? So you basically want to minimize this. So please start with this ln q minus ln q. Now you are having some constraint, right? So we are expressing it as a lambda t gx minus h plus this one x minus b. So these are nothing but some parameter. Okay. So this is your Lagrangian. So what is Lagrangian? Lagrangian basically allows you to, minimize or maximize your function. So you want to minimize this based on your constraint, right? So this is your constraint one, this is your constraint two. So basically, given these constraints, you want to minimize or maximize this function. So that is when Lagrangian help you. Okay. So when you do dl x by dl equal to 0, you get the value of x, which is something like e of ln p minus 1 minus g transpose lambda minus a transpose v. Lambda and v are nothing but parameters, so any random parameter. Okay. So now this is your matrix X. Now, when you put this value again into this equation, so when you put this value of X in this equation, you get. So basically, X.
Hello, Kshitij. Hello. Hello, Kshitij. सब भाग गए हैं. Just wait, Kshitij. Where are you? Hello. Hello, Kshitij.
Hello.